Homework 37, page 373, section 6.4, numbers 3 through 29 odd. 6.4 is all about work. Yeah. Do you guys know? Yeah. Do you know what we mean by that? What is work?
Something work input versus
Physics is what?
I said like work input versus output.
So work is a physics term, and in particular, so work. You think about it as force applied through a distance. So if you have, for instance, and so let's first off let's talk about the units here. Okay, so force itself, one of Newton's three laws. What is it? Force equals something times something.
Mass times acceleration.
There you go. Good. So mass times acceleration. Okay, now let's think about the units on mass. If we're using SI, the standard international units, mass is in kilograms. And acceleration is in what?
Meters per second.
Meters per
Hour per
second.
Squared.
Yeah. Squared, right? Because it's the second derivative of position, right? So meters per second would be velocity. Then you do another per second. You take another derivative, right? Because you have your meters. Let's do time for seconds, right? And then you take the derivative dt, delta t, right? You have meters on the top, seconds on the bottom. That's your velocity. Take the derivative of that, and you're doing that again, divided by time again, and the time ends up all in the denominator squared, right? Okay, so that would be your acceleration. So that's why it's per seconds squared. Or you could think about it as I think about it, which is meters per second, but all together that's meters per second squared. Anyway, oh man, it's leaving streaks. Oh, I'll just continue to use blue, whatever. Okay, so force has units of kilogram meters per second squared. Okay, what do we mean? So let's think about this. You take something that's about a kilogram. This book is about a kilogram, right? And if I accelerate it, that's because I've applied a force to it, right? Okay, but that's not work. Because here I'm going to put force on this wall, like this. And I haven't done any work. I haven't moved this wall through a distance. Right? I am applying a force, but I'm not doing anything. So technically, if let's say you work at a loading dock all day, and you grab boxes here, and you put them over here, if you have not moved them up and down against the force of gravity, technically you have done zero work all day. Your arms will sing a different tune at the end of the day. But technically, you haven't done any work because force has to be applied through a distance for it to be called work. So distance is in what? What are the units on distance?
Meter. Wait.
Again, yep. The standards, the standard international units, it's meters. So if you multiply force times distance, then you have another meters in there. And so it has units of kilogram meter squared per second squared. We call that 1 joule. And a kilogram meter per second squared is called a newton.
Okay.
So units of force are called newtons. Units of work, it's the force, it's a newton applied through a distance, that is called a joule. And so here's the question. How much work is required to lift a 1 kilogram textbook 1 meter off the ground? Or let's just say a displacement of 1 meter. So from, I'm not that tall. Let's go from here to about here. How much work have I done?
1 joule.
It would be 1 joule, right? And it's simple, right? You say, well, if it's 1 because it's 1 kilogram, right? So then the force that I need would be, let's think about this. So if force is mass times acceleration, we're not talking about, in this case, I didn't say how long it took me to do this. It's not the acceleration that I'm applying to it. It's the acceleration of gravity that is equal to the force that I'm putting against it. Does that make sense?
Yeah.
Yeah, it's a little confusing. That's why I'm doing this, because, well, that's why we're going to do a bunch of examples, because this could be a little confusing. When I first thought of this, I thought, well, how much force am I giving? If I give it a lot of force, it actually doesn't matter with gravity. We're not going to get into this, because gravity is what you call a state function. It doesn't matter how much acceleration, like if I move it real fast and then move it real slow. If the only force I'm acting against is gravity, then it works out that it's the same amount of force no matter how fast I moved, because the gravitational field is constant.
Okay, yeah, that makes sense.
It kind of makes sense, right? So when you have these are all word problems, and I'm sorry, but like when you're doing these, like that's just one thing to think about. If you're lifting something that's a certain weight through a certain distance, the only force that we really care about is the force of gravity. So we have the mass, which is 1 kilogram, times the acceleration of gravity, which is 9.8 meters per second squared. That's the force. And then the distance that I've moved it through was 1 meter, so the work is this times the distance, which is 1 meter, oops. And so 1 kilogram, 1 blah, 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 that's 9.8 meters squared, kilogram meters squared per second squared. Or how about 9.8 joules? Okay. So these are the kinds of things these are the kinds of questions you would get in physics if you're not taking calculus-based physics. But here we go. Okay. Rather than give you the spiel, I'm going to give you the spiel after we do this example. So there's an example I made up. A rope weighs 100 kilograms. It's a very heavy rope, okay? And it's 200 meters long. Weighs that, and it hangs off a roof. Of a building. Okay, so here's your picture. Here's your building. Here's the ground. And you have your rope, which is hanging off. And we'll assume, not the rope. And we'll just assume that from the top of the building to the end of the rope is 200 meters. Okay? Question. How much work does it take to pull it up? Now these questions you're going to encounter are like this. There's a lot of assumptions that are baked in here. One of the things is you're not standing here and pulling it up any higher and then bringing it down, you know, stuff like that. We're just going to imagine that you're just pulling it, right? Or like a lot of these are ideal situations. If you really wanted to know exactly, right, you'd have to like figure out the friction in your hands and all kinds of stuff like that. We're just going to say that the work that's being done here, it's just to get this rope to this point here. Now, here's the thing. If I were to just take this rope and I had like a crane or something with a big old arm, and we just took the rope and it's just straight down, and I just lifted it straight up so that the final thing was like this, and I lifted it exactly 200 meters, well then it would be exactly the same thing, right? The force equals the mass times the acceleration, so that would be 100 kilograms times 9.8 meters per second squared. And then I'd multiply it through that distance, 200 meters, and that would be your work. Force times distance is work. But that's not the situation here. What we're imagining is that I'm pulling the rope up from this initial position like this, and I'm going to pull it that way. Again, ignoring friction right here or whatever. And so it starts like that, and then as I pull it up, we get it over here, and now it's come up a little bit. And now we're also going to imagine like it's on the roof here, so the weight is different as this goes up. It starts off with its full 100 times 2, so 20,000 whatevers, I'm sorry. It's the full 100 kilograms, but after I pulled it halfway up, now I'm only pulling up 50 kilograms. In other words, the weight is changing, or the mass is changing as I pull it up. Now that I've said this, and I've already said weight and mass, I want to say, I was going to say this later, I'll just say it right now. Weight is a force. So pounds are force. If I said it weighed 100 pounds, we wouldn't need to multiply it by 9.8. Because pounds is mass times acceleration. It's just always the acceleration of the Earth. So if I say something's 30 pounds, you don't need to take it, that is not a measure of mass. 30 pounds is mass times acceleration already. So in other words, if I would have given you pounds, you don't need to do this part right here. If you're given mass, kilograms, grams, something like that, then you do need to multiply it by 9.8. So that's kind of annoying. But just so you know, like in every one of these, what I'm going to say is find the force, we'll go through it. But when you do that, just remember that weight is itself a force. So if you're given pounds, you already have the force. That's the force part of this force times distance bit that you need. Okay? So it's tricky. Something to keep in mind. But right now, okay, but we don't have weight, we have mass. So we are going to need to figure this out. The thing is now, you could think of work as force times distance whenever everything is constant. Now things are changing as we do this. The mass that you're pulling up, the weight of this is changing as this happens. So yeah, well, this is the way that we're gonna do it. What we're gonna do is imagine this. Any part of this rope, and let's just say, actually, let's use right. This part of the rope right here, let's take a thin little slice of that rope. That part of it needs to move up a certain amount. Like the slice here at the very end needs to go through the entire 200 meters. This slice here doesn't need to go through the entire 200 meters. This slice just below it basically doesn't need to move at all, right? And so if I take this rope and I slice it into tiny little bits, right? Then what we could do is say, well, okay, let's just find a general one. Let's take this tiny little bit right here and figure out the work that it takes just to get that little bit. And so what I've done here is, and I mean, we could think about this as some axis, right? So right here, I guess I'm going the distance I would have to go is 0. The distance I would have to go to here is 200. So this is suggestive of how I might want to lay out my axis and stuff. But if we think about just that little bit of the rope, I want to, if I know its weight and I could compute its distance that it has to be pulled up, which I don't know, let's just say that this is at x. Okay, so here x is equal to 0, here x is equal to like 50, here x is equal to 100, here x is equal to 200, and here x is whatever it is, it's just x. Now let's find the weight or the force of that little bit. So now that I've chopped this up into little bits, let's give each of these little bits a length. What do I want to call this length from here to here? How about delta x? Okay, so that's delta x right there. So that rope, we need to find out how many kilograms are in that little bit. It's the length of it this way is delta x. So how many kilograms are in that little length right there?
100 divided by delta.
Something like that. This is what I'm going to think. There's this concept called linear density, and it's pretty simple. You take the entire length, you take the entire weight, which is 100 kilograms, and we say, well, that right there, divide it by the total length, which is 200 meters. And now what we get is how many kilograms per meter you have. That's a density. It's just not a density in the volume sense, right? Usually, you think about it as mass per volume. This is what we call density, right? Mass per volume. But here, as long as it's not changing, I don't think you have any problems where where it actually changes. They might give you one like that. I don't think you do. But there are problems like that where maybe it's heavier up here and it changes density, it gets thicker or whatever, and so it changes. But in this case, it's constant, right? Because that's all I've given you, so we're going to just assume it's constant. And so in this case, we could say, well, it's a half a kilogram for every meter that you go.
Yeah.
And so in the same way that we could use density, we could say, well, if that's true, and this thing is delta x meters long, then we could say that's 1/2 kilograms per meter times delta x meters, and now we find out that that thing is 1/2 delta x kilograms. So that's its mass, that little bit right there. Everybody got that?
Yeah.
Wait, why do we multiply it by m
Why am I multiplying by what?
again?
I was just keeping track of units,
Oh, it's
right? I'm saying this is my density, and if I multiply, and it's density, linear density, so it's meters, and I'm just making sure that this all works out. But really all I've done is I've just taken 1/2 times delta x.
Okay.
But I'm making sure that the units that I have here are kilograms, because it's not kilograms times distance that we need. It's force times distance. And so that's why I'm taking this step right here, to make sure that now I'm going to need to find a force. Because right now I know how much that weighs. It weighs that many kilograms, whatever delta x happens to be. But I'm looking for force times distance, right? So I'm going to switch back to blue. And say, okay, the thing that I'm looking for, and we'll say we have, n of these, and this is the ith one. And so what I want is the work done on this ith bit. How much work to get this ith bit to get all the way up. And I know that that's the force times the distance for the ith bit.
Yeah.
But right now I only have a mass, so I need force.
To multiply it by 9.8.
There you go, right. So that the ith force is going to be the ith mass times, and the acceleration here is constant because we're working against gravity. So we have 1/2 delta x times 9.8 meters per second squared. So, and I'm going to go ahead and simplify this a little bit. 9.8 divided by 2 is 4.9. So we have 4.9 delta x is my force. So 4.9 delta x is my force. Now I need to find out what is the distance I'm applying it through. I have to take this ith bit and bring it through what? How high?
X.
In this case, the way that I've set it up, it's just x. You may want to set your stuff up with different problems. You might want to set this up as like something, maybe 200 minus x or something like that. But the way that I've set this up, I said that x is 0, and it gets bigger and bigger the further down we go. And so when you're at x, you have a total of x that you need to travel. And so there's that guy right there. Putting all that together, the ith work bit that we have is 4.9 x delta x, like that.
Now we have to take an integral.
And now we're going to add up all of those, right? We're going to say that the total work is the sum of all of those, as I goes from 1 up to n, of all of the works. But I'm going to let n go to infinity, right?
Yeah.
Because n was the number of things that I chopped up. And this is an integral, right? And so the work is then the integral. From where to where?
0 to 200.
Good. From 0 to 200 of what?
4.9x dx.
X dx. Very good. And so I'm going to pull out that 4.9, and I get my x dx, which is 4.9 times what?
1 x squared.
1/2 x squared, evaluated
0 to 200.
200 and 0. That's nice because that works out to
Just
4.9 times 1/2, 200 squared, whatever that is,
4,000.
40,000, I think.
That makes sense.
Oh yeah.
40,000 divided by 2 would give you 20,000, so 4.9 times 20,000.
There's something. Oh, it's 9.8. So it's
So 980,000 joules, and you're like, that's huge, and it is, but that's a very heavy rope, right? 100 kilograms. That's like 200 something pounds. Yeah, I don't know, more than that, to almost 300 pounds, or something like that. 2.3 kilograms or pounds on a kilogram, something like that. So anyway, so that's the idea. So this is one type of problem you're going to see for this. This is where one thing changes. This is where the mass is changing as you're moving something through. But there's a lot of different things that could change, because remember, force is mass times acceleration. And I think the acceleration is probably going to be the same in all of these. And it could be your distance. So any one of these things could be changing as you do this, right? So here, the force is not constant because the mass is changing as we're doing this. And in a sense, the distance isn't constant either, because it's not you're only pulling this part 200 meters. And that's a long way too, so that's why this is so big. Like, it's a huge rope, man. So, yeah, it's not, or no, yeah, it's okay. Anyway, but you're only pulling this bit a little bit, so there's a lot of things that are changing as we do this. And in every case, the way we're going to figure out how much work is done doing something is with an integral. All right, anybody feel comfortable with that? Just want to say one more time that if this were pounds, we would not need to do I went ahead and erased it, but this 100 kilograms times 9.8. We would not need to do that, because a pound itself is a measure of force. And so Force is mass times acceleration, and in SI, the standard international units, you have kilograms times meters per second squared. But that itself is what a pound is. Times some constant, because it doesn't convert perfectly. Some constant, I forget what it is. But that itself, force, is also pounds. So then work, on one hand, when you take distance times that to get your work, with international units, you multiply by meters and you get kilogram meters squared per second squared. But in English units, when we multiply by distance, we use the foot, and what you get is a foot-pound. So work is also in units of foot-pounds. So we have the standard units are joules, English units are foot-pounds.
Okay.
So there you go. And yeah, foot-pound would be how much it takes to move 1 pound through 1 foot, right? That's the amount of energy you expend. This is, by the way, work is energy. That's what energy is. Or it can be converted like it's the same thing. It's how much energy is expended by moving 1 pound through 1 foot. That's 1 foot-pound. And a joule is how much energy is moving 1 kilogram through one well, how much, a kilogram at 9, is it at 9.8? No, I'm sorry, it's not that. It's 9.8 joules is what it is to move 1 kilogram, given that you're on the Earth up 1 meter. So, I don't know. Foot-pounds, that's...
So that's why you weigh differently in pounds on the moon
yeah.
Not-
No,
No,
yeah, yes,
then. Would you weigh the
yes.
same? You would weigh the same in kilograms?
Wait, that'd be different.
You would have the same amount of kilograms.
Yeah.
And so your scale on the moon would have to be calibrated to give you out kilograms. Pounds, I think it's the same thing with pounds. It's like that's calibrated for on the Earth. Only it's 16.9, I think. Pound, what is it? So meters per second squared. So it's like feet per, I think it's second squared, something like that. And so that's what it is on the Earth. I could be wrong about that. And 9.8 meters per second squared. So this is, and so no, it's still the same thing. I mean, it would still be. Oh man, we have so much more to get into. I have to think about that. Your mass doesn't change, but the weight changes. Yes, the weight changes because it's a different constant of gravity acting on you. Okay. So, when force is not constant, we have work to do, right? Up until now, anytime you're given a question like this in physics or whatever, your force has always been constant. This is also like your speed up until you took calculus. Your speed has been constant. When you have, a train leaves the station at this time and travels at this fast. Well, we haven't been able to deal with that. Now we can, and so we're going to have fun with that. Here we go. Here's another thing. Check this out. Hooke's law. Hooke's law says that the force required to maintain a spring, I think that's how you spell maintain. Maintain a spring stretched x units beyond its natural length. I'm going to get into all this.
Oh, I see.
beyond its natural length is proportional to x. That's Hooke's law. So let's imagine a spring. So here's a flat surface, here's a wall, and here's a spring. And let's imagine a mass on that spring, some kind of box or something. Now we're going to imagine that this spring could be pushed this way, or it could be stretched this way. Okay, but right now, he's not moving. This is his natural length. We could also imagine that you have a spring hanging down, some mass that has stretched it to some length or whatever, and that would be its natural length right there. And you could pull it down and stretch it beyond that natural length, or you could push it up and stretch it less than that natural, or compress it less than that natural length. But at any rate, when everybody's at rest, that's its natural length. So I'm going to go ahead and say this from here to here, from 0 up to L, that's its natural length. Okay? Now, what this says is that the force to maintain it stretched some distance, let's call that distance x. So now we've taken this string, we've stretched him out. Look how I'm showing the spring being stretched out, right? Okay, so to maintain this right here, how much force was required to bring him from here to here? Well, actually, it's not the force required to bring him from here to here. We're just imagining I grab it, I do something, and now at this point, now I'm holding it. It should make some sense that if I've only moved it this much, it doesn't take much force for me to hold it there. But if I move it a lot and hold it here, it's going to require more force. Well, it says that that force is proportional to x. So the force needed to move this thing from L over here to L plus x, or x units, is proportional. So it's some constant times x, right there. That's what proportional means, right? That there's some constant times x. And that constant, k, is called the spring constant. And this is actually very accurate as long as you're not doing it too much. Because obviously, if you take a spring, any spring, and you stretch it, it's gonna like deform, right? Like the way that I stretched it here, where you start getting bends in it and stuff like that. Yeah, that doesn't work. So there's a certain range in which this actually works. And if you compress it all the way to the wall and flatten it and squish the metal together, of course it doesn't work anymore. But there's some there's some range in which this actually works very, 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 very well. Okay, and so that's Hooke's law. Okay, so let's do a problem with this. So actually, hold up. So first off, notice now the force is not constant, right? Yeah. From here to here, it's a little bit of force, but as I keep moving it, I have to apply more and more force to get it up to here. So the force that I'm applying here is not the same as the force that I'm applying here. Even though I may be moving at the same speed or whatever, that's not what we really care about. We're talking about the force that the spring, really, it's the force that the spring is exerting on me. That's what we're interested in. Okay?
It's not the mass that's changing this time.
Yeah, the mass is not changing this time. The force is changing this time. I haven't said anything about mass. That changes things a little bit. But, I mean, it doesn't change this. It's just that adds more flavor to the problem that you're working on. And you'll see, if you go on, you'll have plenty of those. So, let's do this. While we're talking about springs, let's use little f to be the force of the spring. And as you can see, it's a function of x, right? It's a function of, if we're using x to denote how far this thing has been moved. And you'll notice, like, once you set something like this up, it's probably in your benefit to say, well, why don't we call the natural length, whatever that is, why don't we call that guy 0? Because I could call, this is my x-axis, and I could call it anything I want. instead of dealing with trying to plug in an L plus X and blah, 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 it'll just be easier to do this right here.
Yeah.
So that's what we're going to do. So, okay, here we go. Here's the type of question you're going to have with this. Kx, some constant. We don't know what the constant is. That's usually the first thing we have to figure out with these types of questions. So, here we go. Here's number 10. It says, that's not what it says, if. It doesn't say that. Find the work. Oh, no, it is if. I'm sorry. Okay. If the work required to stretch a spring one foot beyond its natural length. So I'm already imagining you have some spring. It has some natural length, L. And now we're talking about stretching it 1 foot beyond that. Okay? Beyond its natural length is 12 pounds. Okay? So you've taken a spring, you've stretched it out 1 foot, and that work right there is 12 pounds. Notice that's force, right? That's force. Pounds is force. Okay, so that's good. We're good. The question is, how much work is required to stretch it only 9 inches?
Just 3/4.
You'd think, well, that's 3/4 of that. It's 3/4 of 1 pound. It should be 3/4 of a pound, right?
But it's exponential. I mean,
Yeah.
the force changes.
But yeah, and that's the problem is that the force is changing. The force is only 12 pounds out here at a foot. But if you've stretched it 9, well, it's less than that, right? It's not, and you're thinking, well, yeah, 3/4. No, let's figure out how we're going to have to work this out. First off, we're talking about a spring, and so we're in this domain right here. So let's think about this. Let's just do this part right here, because it gives us the work, and we know that the work in this case is going to be a sum of a bunch of little works. So let's do that first. Let's say, here's the spring's natural length. I'm going to call that 0. And I know that if I stretch it out to 1 foot, the total work it required to do that was 1 pound. No, I'm sorry, 12 pounds. But that work is a sum of little works. So let's figure that out. Because this is what I'm saying. That total work was done was a bunch of little works. It was the force right here moved a total of delta x. Right? And then it was, well, then now that you're out here, so if you imagine what you're doing here is you have some spring, some box, and we haven't moved it at all. Now, to move it delta x in this direction, that required some amount of force applied through some tiny distance. But now we're at this distance. We haven't got to 1 foot yet. 1 foot is infinitely far away, really. And now, okay, now that you're here, we pulled it another delta x. But the force was stronger because we pulled it further. But we've only pulled it through delta x right there. Okay? Now, and so that's another one of the works that we're adding up. We're adding up the sum of all these little works. And you do this and you do this, and now you're out here at xi. You're at the ith little bit. And we're going to say, okay, your box is at xi, and you're going to pull it some small amount delta x. And that small amount delta x is so small that it's pretty much, then the force around there is technically constant. Or good enough, close enough to being constant.
Yeah.
Right? Then that's the hack that we're using here, right? We're going to
It goes
say,
to infinity, so it's going to be, right?
what's that?
When it goes to infinity, it will be constant, right?
Right. When we let this get infinitely small, then at that point it will be constant. So when we let x get really, really, really tiny, but we're starting off with our approximation and saying it would be enough to just do this, say, 100 times, and we'll say so from 0.5 feet up to 0.00 whatever feet. How much work? Well, it's about this. It's about this much force, and so it's constant there. And then when we take the limit, it'll be good enough, or it'll be exact, really. Okay, so that's the idea. So let's find the work that's needed here at xi to go from xi to xi plus delta x. Okay, so work is what times what?
Force times distance.
Force times distance. Okay. Now, if we're at the x, and we'll just call it x, we're at x. So then what's my force here?
It's 12. K.
It's kx. We don't know what k is yet. That's what we're going to need to find out here. That's part of this. We don't know what k is, but if we know that the work is this, and so kx is the force here at x. And what's the distance through which we're going to pull this little bit?
No, delta x.
Delta x. Yeah, there you go. Now, that's the work that it took to take this box from x and move it delta x that way. And so, we're going to add all those up and find the total work. And when we do that, when we take that limit, we get the integral of this thing. So that the total work is the integral of kx delta x, which goes to dx. And we're integrating from where to where?
0 to 1.
0 to 1, because x, we started at 0 and we pulled it out to 1. So from 0 to 1. And so k is the constant, we're going to pull them out, and we have the integral from 0 to 1 of x dx, which is equal to k times what?
1/2 x squared. Evaluate from 0.
Which is what?
Just k1.
Yep, a half k. Okay, so that's the work. But the work, they told us, was 12 pounds.
Yeah, so 12
So
pounds.
1/2 k is 12. Now we know that k is 2 times 12 is 24. Now we can get to the actual problem. Okay, so that was all just, and this is how you do this. This is always like this. They always tell you something like this, so that you have to go find what the spring constant is. So this spring constant is 24, whatever's it would be. The force is pounds. So let's see. Force equals kx, and x is in feet, and force is in foot-pounds.
That's pounds.
No,
Right.
force is in pounds. Force is in pounds.
Yeah. Okay. So then
Then
it's,
k is pounds per foot.
yeah.
So k pounds per foot. 24 pounds per foot. And you're like, but it was 1 foot and it's 12. Yeah, because it's not constant.
That's what I'm.
Oh, okay. Oh, you going?
Yeah.
Awesome. Here, I'm gonna say hi to you. Oh, hi. I thought it was gonna be his mom, and I was gonna be like, we don't want to be. So anyway, hi. Or your mom. I said his mom, so it's not your mom. Have a good one. See you guys at co-op.
Yeah, thanks.
All right. Okay. Okay, where were we? We found the spring constant. We said that K is 24 whatevers. And really, I don't care. Pounds per foot, whatever. All right, now let's get to the actual problem. So now we want to know how much work is required. So now you can think about this as like a completely different problem here. They could have said, if the spring constant K equals 24, how much work is required to stretch for a given spring, for some spring? How much work is required to stretch it 9 inches? And of course you'd have to be told that this is that K is pounds per foot, I guess. But anyway, okay. So again, this is just work, right? Work is, we're gonna add up all the little works because it's a spring constant. The force is not constant as you change. And so we're gonna have to do some calculus and say, okay, the work is the force times the distance. And we're taking, and I love using pictures here. I'm not going to mess this up if I draw a picture. So we're starting at 0 and we're going to move it out to 9 inches. But given that all of this was done in feet, 9 inches is how many feet? 3/4 of a foot, so up to 3/4. There we go. Right. Now, if I just wrote that for some spring and then I told you this, you'd probably assume that this is given in inches. You know what I mean? It's that the context from the previous problem, we know that 9 inches is in feet or whatever. So be careful. I haven't looked too carefully at all of the problems. They might have tried to mess with you like that. Be very careful with these. But at any rate, okay, so we're going to imagine, okay, hey, I know the force changes as this goes because the force as a function of x is actually k times x, so that's 24x. And so I'd better think about the ith one of these. So when we're here at x and we move him by delta x, a distance of delta x, that's the problem I'm going to use for the ith one of these. And say, okay, when you're at x, the force is 24x. That's not too bad. So 24x. The distance through which I move it is what?
Delta X.
Delta x. And that's my, one of my works. And so I want to sum up all of my works to get the total work. And I want to take the limit of the sum, which gives me the integral of the thing. 24x delta x becomes dx. And we're integrating from where to where? 0 to 3/4. There we go. Alright, so that's 24 integral x dx, which is 24 times, we've done this a bunch of times now, 1/2 x squared up at 3/4, down at 0. That 0 is really nice, so then the 3/4, this gives me 24 1/2. 3/4 squared is the same as 9/16. There's a 2 here, and that gives me 12. Right?
You could
Right.
just do, it's 936, which is 4, and then 4 times
Okay.
24.
Good for you for being able to do that. Okay. 16 and 12 is 3 times 4 times 9. 16 is 4 times 4.
Yeah.
Is that what you said? 27/4? Is that what I got? Yep,
Yeah,
27/4. There we go. It's not 3/4 of the thing, right?
Yeah.
Wait, earlier it said, well, if it's 1 pound, 1 lb, that looks terrible. 1 pound to do 1 foot. Well then, how much if you have 3/4 of a foot? You'd think it's a 3/4 of a pound, but it's not, because it's not. It's not constant. And that's what's tough about this stuff. Okay. So here's the thing. I don't want to write this up here, but I'm going to do it. And I'm only going to write it up here to say, in fact, what I wrote on my paper was, don't marry this definition or this setup that I'm about to write. Because you can think about it this way, but as we just saw, like, we did 2 different work problems, and they were different. It was like, ultimately, yes, we found the individual works and did stuff, but I'll just write this up. So on one hand, we could think of work as the integral from over some distance, f of x, just dx. And that's what it worked out with the spring constant, right? Where the force was variable. Yeah. Force, F, is variable. On the other hand, work, with the rope setup, the force was variable, but we didn't have a function describing it, right? And so what we did is we added up the individual works. We had a constant, actually the force itself wasn't constant. The acceleration, gravity was constant, right? But we didn't have a function to do that. So what you could say is like, with a spring constant, it's like this, right here. You have this right here. Though, this could be subtle too, right? So what I'm getting at is, don't think about it this way. If you just, the same way with like finding volumes and stuff, I'd say every time you find a volume, break it up into the ith volume and then add all of those up. I recommend doing the same thing with work. Like with every one of your problems, break it up into the work to do an infinitesimal amount of it and then add all of those up. Don't marry yourself to something like this. Although, with almost all of the spring questions, it boils down to this. But they could be subtle, and they could throw you through a loop, and it doesn't quite work out as simple as, because you have this idea like, hey, if this spring constant is 5, then this is that, and now I just integrate that, and it's like, yeah, but they could throw some subtleties in there that will mess you up. So I recommend, don't marry this right here. Think about it more like this. And so, okay, now for the hard part, the part that I have not rehearsed. I wanted to do this on the fly because I wanted, yeah, that's right, I didn't write it out. I want you to look at this. Okay, so first off, before I say this, example 5 on page 372, example 5. I highly recommend that you go read that and make sense of it. It is this type of problem that we're about to do, and they have a way of doing it that is very elegant, and it probably would have made your life a lot easier when we're trying to compute volumes if you knew this right here. I don't do it that way. I almost refuse to do it that way because it only works with like cones. You know, and but it is so simple. And like if you do it my way and then do it this way, you'll be like, that saved me like 15 minutes. Yeah. And you know, while that's really cool, it only works for cones. And so I don't like to do it that way, but do read it because it might make some of your problems in here a lot simpler. I'm not going to let you choose. I'm going to do this myself. So, Here's the problem. We have a water tank full of water. And I'm going to do number 24. A water tank is full of water, and here's the shape of the tank. Flat on the top. It goes down 6 feet. And then it's a ramp this way. Okay, so that's flat with the earth or whatever. And then it drops down 6 feet. And it's 10 feet this way. And 12 feet this way. Now, since it's given in feet, I'm thinking, okay, foot-pounds is the way I'm going to do this one. The question is, how much work does it take to pump all of the water out of the top of this thing? Now, in some of the problems, let's just think about the tank this way. In reality, what you'd be doing is you would have some kind of spigot right here, right? And you have a hose that runs down to the bottom or something like that. And we're going to pump this guy out that way. And so this itself has a height. And I think you have one where it is a setup like that. It's a trough. Oops. It's a trough like this. It's a V-shaped trough. This is one of your homework problems. And it actually does have a spigot right there. And you have to figure out, given that that spigot is 2 meters tall, you have to take that into consideration. But when they don't give you one of those, we're just going to assume that this is negligible, right? So for the water to come out, it's negligible, and so we only need to get it up to that high right there, which in this case is 6 feet. We need to take it and get it out. Here's the problem. The water that's right here needs to go this distance, but the water that's, say, right here only needs to go up that distance right there. So now the distance is variable.
Yeah.
Right? The water weighs the same amount. Right. And does it tell us? Yeah, it says use the fact that water weighs 62.5 pounds per foot cubed. So we're dealing with volumes, okay? And what we're going to do is the same thing we've been doing, is think, okay, hold up. It's not just, because we're not grabbing this entire volume and lifting it all up, just like with the rope, right? We weren't taking the entire rope and lifting it 200 meters. It changed as the amount that we had to lift changed. So here, we're going to have to take, we can imagine cutting it in slices, in vertical slices. Now we don't have the option of which way we want to slice up this volume. It used to be, like when we're just, if you're just trying to compute the volume of this thing, you could say, well, I cut it up any way I want. I could cut it up this way, and if cutting it up this way makes my calculations easier, that's great. Now we have to consider that the volume that we're lifting, the distance we have to lift this volume is constant along the height partition, right? So everything that's this high, or low, I guess below the ground, if you want to think about this as the ground, right? Everything that's this low has to be brought up that much. And so we have to treat that bit like one unit together. So we're going to partition this thing into volumes. Okay, and let's just kind of think of the overall thing that I want. I want the work, the total work, which is going to be a sum of the individual works. And the work is going to be a force times the distance, But the force, in this case, is going to be the mass, or the weight, of this moved through some distance up this way, right? So always it's a force times a distance. But in this case, we're going to need to find the weight of one of these bits right here. And so that's, in order to get that, we have pounds per foot cubed. And so if we know the volume, right, just like with linear density, if we know the volume per foot cubed, right, so we have, we have the density, and if we multiply that by the volume in feet cubed, then we'll have the force, because pounds is force, okay? So that's the thing that we need to find. We need to find the volume of this slice right there. So let's think about this. I'm going to take my total volume, chop it up vertically, and now I have the ith slice. I'm going to call that volume I right there. And there's a few different ways I could do this, I guess. This is the thing that's been partitioned, the height. Do we want to call that x, or do we want to call it y, or what do you want to call it?
Delta.
Let's call, okay, so let's give this a name. Let's give this vertical axis a name. We'll call it the x-axis. And we'll say, okay, so when we're here at x, we want to find the volume as a function of x. Now here's the question. Do you want 0 to be up here and 6 to be down here, or do you want 6 to be up here and 0 to be down here?
6 up.
You want 6 on the top. Okay, let's do it that way. So 0 is here, 6 is here. So what's the distance going to be then in terms of x?
Wait for the whole thing.
Well, hold on, we're at x.
Oh,
now we have to lift
6
him from
minus
here.
X.
There we go. Okay, so then the distance is 6 minus x. Okay, all right. Now, here. So that's one way of doing it. And we'll see what that does up here. Another way we could have done it is said, okay, well, if I call this 0 and call this 6, then if we're here at x, then the distance that I have is just x to lift him up through. I don't know which one's easier. It might work out. I mean,
Like a negative area.
I mean, I don't know. I don't know. If we set everything up right, it should work just fine. It's just how do we want to do it, right? So let's think about it this way. Let's do it this way, and we'll see what happens. Okay, so now that's the distance that I have. That's my di right there. Oops. Now we need the volume. Now that volume. Now I'm going to consider it. Here's my x. We have this length, which is always 10, and this guy comes over to here, and everybody who's in here is just a rectangle, right? So what's the height of that guy? The delta x. Okay, so delta x. This slice that I just took, it's like this. We know that its thickness here is delta x. We know that its length this way is 10, so that's easy. Now the hard part is finding what's that guy right there. And if we're doing it this way, oh, we also know that this total bit is 12. If we're doing it this way, I would say, think about, can I get this thing, whatever this is, because that's like the height, if I could get that as an output. So when x is 0, it's 0. When x is 6, so notice what I'm doing, right? X, we decided to name the variable, the thing that's changing, x. So I want to put x on this axis. Now that I've done that, it looks like this. I plug in a 0, I get out a 0. And then when I plug in a 6, I get out a 12. There we go. So that's that. I've just flipped it, right? And when I'm at x, now what's that height? This is y equals mx plus b. B is 0. That's nice. So what's my m?
12 over x.
12 over what?
12 over 6.
12 over 6. 12 over 6x, which is just 2x.
Okay.
So that height right there is 2x, which means that this distance right here is 2x. Which means that that depth right there is 2x. So now my volume, my ith volume is what?
2x times 10 times delta.
There you go, 2x times 10 times delta x, or we could rewrite that as 20x delta x. Not too bad. Let's look at what would have happened if I would have named it the other way. That is, if I would have said, okay, why don't we call this guy 0 and this guy 6, in which case di would have just been x, right? We said that a second ago,
Yeah.
right? Because if we're down here at x, then the distance that we'd have to lift it is whatever x is.
Yeah.
When it's 6, we have to lift it 6. When it's 0, we don't have to lift it at all. When it's somewhere in between, it's just x. Okay. Now, though that I've called it that way, when I go to say, okay, my input is x, I want this length to be my output. Now I plug in a 0, I get out a 12. I plug in a 6, and I get out a 0. Plug in a 6, get out a 0. So then the line is this thing. Now, y equals mx plus b.
12 over 6.
Yeah, it's 12 over 6, negative 12 over 6 x plus 12.
Yeah.
So you're not getting away from it, right? We have, this is negative 2x plus 12, which you could rewrite as 12 minus 2x. And over here you'd have a negative in there, but your di wouldn't have a negative in it. Here we don't have a negative in here, but your di does have a negative in it. So there's no way around it. Like, you know, it is, and I wanted to show this, right? Like, if you choose to set, you could choose to set it up either way, but there's going to be trade-offs, and the trade-offs are about the same either way. So it's not going to matter. It happens to be that the way that you said to do it worked out to be easier than trying to figure this out, as far as I'm concerned. But either way, it's going to be ugly. These problems are just ugly. Okay, so that's the volume, but we're looking for force. And how do we say we find the force?
Multiply by weight of water.
There you go. So in other words, 62.5, that's pounds per foot cubed times the volume, the ith volume, which is in feet cubed. So that's 20x delta x feet cubed. Feet cubed cancel, and I'm left with 62.5 times 20, 0, 0, 0, 10, 4, 5, 12. Point, so 1250.
Yeah.
Is that right? 1250?
Yeah.
So 1250
X
x delta x, feet are gone, it should just be pounds. That's how many pounds, that's the force that's required to lift that slice that high. And now what we're going to do is add up all, thank you, now that's the force, that one of those, that's how much it weighs. Now we need to multiply it by a distance to get that. So this was force, the ith force, right there. Now we need to multiply that by the ith distance to get our work. So 1250x, delta x was the force. The distance is 6 minus x. That's how far we need to lift it. Okay, you know what I'm going to do? I'm going to rewrite that as 1250 times x, 6 minus x, delta x. You like that?
Yeah.
I like that. Okay, so that's how much work it requires to lift that thing that weighs this much, that slice that weighs this much, a total of 6 minus x feet. That's the work. Now we're going to add up all of those right there. I'm going to get rid of all of this stuff that we've done. Make sure I don't want to mess this up. Yep. We took that. That's the slice that we're lifting that high. Okay. Okay, so the total work is the sum of all of these works. And so the total work is the sum of all of the works, but we're going to take the limit of the sum, which is then an integral of this stuff right here. So we have 1250 x times 6 minus x. Delta x becomes dx. And we're integrating from where to where?
0 to 12.
Remember, x was this guy.
If
Right.
you plug in a 6, won't it just be, everything will be 0?
If you plugged in a 6, we're not plugging in a 6. We're taking an integral of this function from 0 to 6.
Okay, yeah.
Right? And that order shouldn't matter. The way that we did this, now here's another thing we have to think about, is we called the bottom 0, we called the top 6. Do we integrate from 0 to 6? It shouldn't matter. It shouldn't matter how we do that. It should go from 0 to 6.
When you have a negative, if you switch it.
What now? Yeah. If we did it the other way, and this is honestly, if you get to the end and then you have a negative number, then you've done it the wrong way. But the thing is, we called this 0, we called this 6. We should go from x going from 0 up to 6.
Yeah.
Shouldn't go from 6 to 0 because... Well, this remember how when we did the d the other way, the other thing became negative, right?
Yeah.
So this should take care of it. Yeah, and if you think about what does this function look like? It goes here, it has a 0 at 0, it has a 0 at 6, it's a parabola, and so it does that. And so we're going to be adding up positive area, which makes sense. It should be positive work. So, yeah, there's something to think about. So, okay, let's pull out the 1250. And we have the integral from 0 to 6 of, I'm going to go ahead and multiply this out. That's 6x minus x squared dx, which is 1250 times, okay, antiderivative of 6x. 3x squared minus 1/3 x cubed. We evaluate that up at 6 and down at 0. That's nice. The zeros go away. We're going to have 1250. The 6 goes into here and becomes 36. So that's 3 times 36 minus off 1/3. 6 cubed, that's 36 times 6 is 36. That's 8. 3 times 6 is 18.
Yeah.
21. 216. So that's 216 over 3. Yeah, we're good. That's how much it is. Whatever that works out to be, I don't care. It does look like that should be positive. Let's just make sure.
Yeah.
3 times 36 is 18, 9, 108, 108. Yeah, 9 and 108 minus 216 over 2 would be 108. So over 3 is less than 108. So yes, that is a positive number. We're good to go. Yeah? Yeah. And if you did get a negative number, then you probably messed something up with your order of integration. But that's another problem here is you have to be very careful when you get to this point. If you, let's say we did get a negative number. Hey, could you guys keep it down a little bit, please? Please keep it down. Thank you. So another thing you'd have to worry about is, did I set up the distance thing the right way? Right? Because when we had this like this, and we said, okay, then the total distance you needed to lift it, if we were calling this 0 and 6, then the distance we need to lift it, and we're here at x, was 6 minus x. And I'm sure we did that the right way. And so I feel confident about that. And so then if I ended up with a negative number at the end, I'd say, oh, maybe I should have integrated the other way. Right? But if you do, and so then you look in the back of the book and go, oh, it should have just been negative. I should have flipped that around. Although it shouldn't matter. Well, I mean, it would matter because if you flip it, it becomes negative. But anyway. But if you get to the back and it's a different number, then you probably messed this part up somewhere. Like if you just go, oh, the distance is x, right? From there to there, the distance is x. It's not x. But if you did that, let's just see what would have happened. Like how different would this have been had you made that mistake? If you said, you know, you're back over here and you say, okay, then the distance from here to here is just x. It's not, it's actually 6 minus x. What you would have ended up with was 1250 times x dx. You get 1250 integral of x squared, which would be 1250 times 1/3 x cubed, which we just figured out was 216 over 3, 1250 times 216 over 3. You're going to get something way different than what you got over here. And then you know, oh, okay, I probably messed up my distance somewhere because that's like the hardest part of all of this. Okay? So, please, so the volume thing, if you were good at calculating the volumes in the last, that we were doing, this shouldn't be too hard because it's really, that's all you're doing. You're calculating how do I find the volume, then you're just multiplying it by a distance, or well, a volume times a density really, but it's the same ultimate setup. The hard part is finding the function which describes the volume and integrating that guy. But once you find that bit that describes the volume, you'll multiply it by your density to get your actual weight or your force, and then multiply that guy by the distance. The distance is the really, really tricky part. Lots of different things. We don't really have time to do number 22, but I'll kind of set it up for you. Same problem. There's a tank with water. How much force to get all the stuff out? Only now the tank looks like this. It's a spherical tank. It has a radius of 3 meters. And it has a spigot that is 1 meter long. And so we're going to be we have to chop it up this way. We have no recourse otherwise because we are lifting that much volume through there. We're not lifting this much volume. Or you could try. if you want, but then you'd have to figure out, well, this weight is a different amount, and this weight is a different amount, like that's a different distance we have to pull it up through. Much easier to just say, okay, let's take this slice right there. 3 meters, and so this guy has a volume of, oh, that's not 3 meters. We don't know, that's the problem. Right, and so we need to know the radius there. The volume is going to be, we'll call this delta x, I guess. Delta x. So pi r squared dx is the volume. Multiply that by its, and you see now they've given it in meters. I would look through the book and find when they give you the conversion for, or you might have to convert it yourself. Meters. They give it to you. Density of water is 1,000 kilograms per meter cubed. 1,000 kilograms per meter cubed. So that's how many, and of course this r here, we're going to call it a function of x, and that function of x is root 9 minus x squared, right? Because that's what gives us 3, negative 3, and 3 right there. Plug in a 0, you get out a 3, yep, that's it. So then the radius is that guy right there. So my volume is pi times 9 minus x squared, delta x. That would be my ith volume. That volume, we need a force. And this is, I'm glad I did this, because it's not just that, that's not a force, right? We have to say 1,000 kilograms per meter cubed times VI, which is this, which is meters cubed. So pi 9 minus x squared delta x meters cubed. But now we just have kilograms. So that's 1,000 pi 9 minus x squared delta x kilograms. We still need to multiply that by the force of gravity, or by the gravitational constant, which will give you 1,000 pi 9 minus x squared x kilograms times 9.8 meters per second squared. So that gives you 9800 pi 9 minus x squared delta x kilogram meters per second squared, which is force newtons. That is what you need to do there.
Yeah.
So that's your ith force. Now we need to move it through what distance? Well, that depends on how you want to set this up. I guess the way that I've set this up here, x goes from -3, right? There's -3 all the way up to 3. So then x would be, if x is here, x minus -3 would be the distance that I need to multiply it through. -3. Minus -3 would be x plus 3. When x is 0, you gotta go a total of 3. When x is 3, you gotta go through 6. Does that make sense? Yeah. So that's tricky. So then finally, your ith work is your ith force times your ith distance. So that's 98 pi 9 minus x. The distance is x plus 3 delta x. And that's the thing that you're integrating. Yeah. So, have fun with this.